Look up at the night sky on a clear, dark evening. You see a tapestry of stars, distant and serene, a picture of cosmic tranquility we've all grown up with. But what if I told you that this peaceful vista is an illusion, that beyond what our eyes can see, the universe is a chaotic artist studio filled with bizarre, colossal structures that defy the very laws of physics as we know them? These aren't just stars and galaxies, they are cosmic puzzles on an unimaginable scale, mysteries written in the fabric of space and time that leave even the most brilliant astronomers utterly bewildered. We're about to embark on a journey to explore 25 of the most enigmatic and mind-bending galactic structures ever discovered, from colossal rings of galaxies that shouldn't exist to vast, silent voids where nothing should be. This is the real, untamed frontier of our understanding, a place where every discovery raises more questions than it answers. Think about the feeling of looking at a complex lock, knowing there's a key somewhere, but having no idea what it looks like. That is the profound and thrilling position we find ourselves in today. We have mapped the cosmos, peered into its deepest corners with our most powerful telescopes, and yet we keep finding things that simply don't fit. These aren't small anomalies or minor errors in calculation. These are galactic-scale head-scratchers, structures so vast and so strange that they challenge the foundational pillars of modern cosmology. They whisper of forces and phenomena we have not yet begun to comprehend, hinting at a universe far more complex and wondrous than we ever dared to imagine. This video is your guided tour through this cosmic cabinet of curiosities. We will traverse the expanse of our own Milky Way and venture far beyond into the deep field, confronting these magnificent puzzles one by one. You will witness the impossible, question the established, and feel that spark of awe that comes from standing at the edge of the known, looking out into the great unknown. It's a journey of collective human curiosity, a story of our relentless drive to understand the cosmos we call home, and it all starts right here, right now. So let's begin. Our journey begins not in some distant corner of the universe, but right here in our own cosmic backyard, with a structure so vast it redefines our understanding of the Milky Way's recent history. For decades, we gazed toward the center of our galaxy, focusing on the familiar band of stars and dust, completely unaware of the gigantic ghost haunting our galactic core. Then in 2010, astronomers analyzing data from the Fermi Gamma Ray Space Telescope made a staggering discovery. They found two enormous symmetrical bubbles of ultra-high energy radiation blasting out from the galactic center like the echoes of a primordial explosion. These are the Fermi Bubbles, and their scale is almost incomprehensible. Each bubble stretches an astonishing 25,000 light years from the galactic plane. To put that in perspective, if you could see them in the night sky, they would span over half of the visible sky, from the constellation Virgo all the way to Grus, the crane. We're living inside a galaxy that, on a cosmic timescale, very recently blew a pair of colossal, energetic bubbles, and we only just noticed. The most compelling question, of course, is what created them. The prevailing theory points an accusing finger at the supermassive black hole at the heart of our galaxy, Sagittarius, a star. The idea is that millions of years ago, this sleeping giant woke up in a violent fury, consuming an enormous amount of gas and dust in a single, epic feast. This accretion event would have been so energetic that it launched two powerful jets of material and radiation, shooting perpendicularly out of the galaxy and inflating these massive cavities we see today. It's a dramatic story of a dormant monster roaring back to life, but there is a competing and equally plausible explanation. Perhaps the bubbles weren't carved by the black hole, but were instead forged in a fiery period of intense star formation. In this scenario, a wave of millions of stars being born all at once in the galactic center would have generated powerful stellar winds and a cascade of supernova explosions. The combined energy from this stellar frenzy could have blown a gigantic, bipolar superbubble into the surrounding galactic halo. So which is it, a black hole outburst or a starburst? The debate is fierce because the evidence is tantalizingly ambiguous. The bubble's sharp, well-defined edges suggest a sudden, short-lived eruption, which favors the single black hole event. However, the specific composition of the gamma rays and other particles within the bubbles also matches what we'd expect from a sustained period of star formation. This isn't just an academic disagreement, it cuts to the very heart of how galaxies evolve. Are these colossal structures primarily sculpted by the violent whims of central black holes, or by the collective booming birth of stars? The Fermi Bubbles stand as a silent, monumental testament to a cataclysmic event in our galaxy's past, an event whose true nature remains one of the most captivating and unresolved puzzles in modern astronomy. Leaving the colossal, energetic Fermi Bubbles behind, we now turn our gaze outward to a structure of such serene and perfect geometry that it seems almost too beautiful to be natural. Nestled within the constellation of Serpens, 600 million light-years from Earth, lies Hoag's object. Discovered by astronomer Hoag in 1950, this galaxy is a breathtaking cosmic anomaly. At its heart sits a perfectly round, dense core of ancient yellow stars, glowing with the warm light of stellar old age. Surrounding this core is a pristine, ethereal ring of brilliant blue, a circlet of much younger, hotter stars actively forming. The most striking feature, however, is the profound, dark gap that cleanly separates the two. It's a near-perfect circle of starlight floating in the void, a celestial donut that defies the chaotic, spiral-armed norm of most galaxies we observe. The formation of such a perfect ring galaxy presents a profound puzzle. Our standard model for these structures involves a galactic collision. The classic example is the cartwheel galaxy, where a smaller galaxy has punched straight through the center of a larger disk galaxy, sending a rippling shockwave of dense gas outward, which then triggers star formation in a brilliant, expanding ring. But Hoag's object shows no evidence of a perpetrator. There is no second galaxy nearby that could have been the intruder, no trail of stellar debris, no distorted core suggesting a recent, violent impact. It sits in majestic, solitary perfection, offering no clues to a violent past. So, if not a collision, what force could have sculpted this cosmic marvel? One compelling theory suggests a different kind of drama, a slow gravitational dance and eventual merger that happened billions of years ago. In this scenario, a small, dense companion galaxy was gradually captured and torn apart by the gravity of the larger central galaxy. As it was shredded, its stars and gas were scattered into a vast, unstable disk around the core. This disk would have been prone to a phenomenon known as a resonance, where specific gravitational frequencies in the disk amplify the clumping of gas. Over eons, this resonance could have organized the gas into a single dense ring, far from the core, leaving the clear gap we see today. The ring then ignited with the birth of new stars, while the core was left with its original, older population. Another, more exotic idea posits that Hoag's object might be the result of an extreme instability within a single primordial cloud of gas, as it was first collapsing to form a galaxy. Under very specific and rare conditions, the rotating disk of gas could have spontaneously separated into two distinct rings, with star formation prohibited in the gap between them due to the specific gravitational forces at play. This would make Hoag's object a unique, one-off event, a galaxy born perfect from the very beginning. The haunting beauty of Hoag's object is that it offers no easy answers. It stands as a testament to the fact that the universe can create order and symmetry through multiple, mysterious pathways, some violent, some slow and resonant, and perhaps some we haven't even begun to conceive. But our own galaxy holds more than just the ghosts of past explosions. It is also caught in a relentless cosmic current, pulled toward a mystery hidden in plain sight. For decades, astronomers have known that our Milky Way is not drifting aimlessly through the cosmos. It is moving along with our entire local group of galaxies at a staggering speed of over 600 million miles per hour towards a specific, unseen point in the sky, deep in the constellation Centaurus. This mysterious focal point of our galactic journey has a name that evokes its profound power, the Great Attractor. Picture the entire mass of our galaxy, with its hundreds of billions of stars, being irresistibly drawn towards something we cannot even see properly. The core of the mystery lies in its location. The direction of this immense pull happens to lie directly behind the plane of our own Milky Way, in a region astronomers call the zone of avoidance. This is the thickest, most crowded part of our galaxy, a dense band of interstellar gas cosmic dust, and countless stars that completely obscures our optical view of the universe beyond. It's like trying to peer through a dense, foggy forest to see what lies on the other side. Our own galactic backyard is blocking the view. For a long time, this meant the Great Attractor was a gravitational phantom, an anomaly we could infer from our motion but not directly observe. The key to piercing this veil was to look not with visible light, but with wavelengths that can penetrate the dust. Radio, infrared, and most importantly, X-ray telescopes became our cosmic eyes. Projects like NASA Rosat and later observatories began to map the hidden universe, and what they revealed was astonishing. The Great Attractor is not a single, unimaginably dense object, but rather a colossal concentration of mass, a gravitational focal point on a scale that is difficult to grasp. We now understand it to be the core of the Laniakea supercluster, a vast filament of over 100,000 galaxies, including our own, that stretches across 500 million light-years of space. At the heart of Laniakea lies the Norma cluster, an immensely dense knot of galaxies and dark matter, which acts as the central gravitational anchor for our entire supercluster. This is the primary source of the pull, yet the story deepens further. Even this enormous supercluster seems to be part of a still larger flow, pulled toward an even more massive and distant structure known as the Shapley Attractor, the greatest concentration of matter in our observable universe. So the Great Attractor is not one but many things. It is a destination, a signpost, and a humbling reminder of our place in the cosmic web. We are like leaves in a vast river, feeling the current pull us toward a nearby waterfall, only to discover that the entire river system is itself flowing toward an ocean. It is a cascade of gravitational influence, revealing a universe structured on scales so vast that our entire galaxy is but a single speck in an unfathomable current. Yet for every colossal structure we can map, there remains the haunting possibility of something far more subtle, a fleeting whisper that suggests we might not be alone in the cosmic ocean. On a sweltering Ohio evening in August 1977, a quiet revolution in the search for extraterrestrial intelligence was underway. Astronomer Jerry Amon was volunteering for the SETI project at the Big Ear Radio Telescope, meticulously sifting through reams of computer printout data. The telescope was performing a systematic scan of the sky, listening for any narrowband radio signals that stood out from the natural background hiss of the universe. Then his eye caught a sequence of letters and numbers that made him catch his breath. He circled it in red pen and in the margin wrote 3 letters that would become legendary: WOW. This was the WOW signal, a 72-second burst of radio waves that remains to this day the most compelling candidate for a potential artificial transmission from beyond our solar system. What made it so extraordinary was its precise profile. It was a powerful, narrowband signal concentrated around the frequency of 1,420 megahertz. This is no random number. It is the emission line of neutral hydrogen, the most abundant element in the universe. The logic behind listening at this frequency is profound. Any technologically advanced civilization seeking to announce its presence would likely use this universal landmark, a sort of cosmic watering hole where all species might logically gather to listen. The signal itself was a clean, intense spike, rising and then falling in strength over the 72-second window, exactly as you would expect from a distant, fixed source passing through the stationary telescope's field of view. It was over 1 billion times more powerful than the typical background static of space, a clear and unmistakable siren call. The immediate assumption was that this was it, the moment humanity had dreamed of for centuries. But then nothing, despite dozens of subsequent searches by the Big Ear and other powerful radio telescopes over the decades, the signal never repeated. It was a one-time event, a cosmic flash in the pan that has stubbornly refused to show itself again. This singular nature is the core of the enduring mystery. If it was an artificial beacon, why did it only transmit once? The hunt for an explanation has been a graveyard for theories. The most obvious culprits were quickly ruled out. It wasn't a signal from a passing satellite or aircraft, as those move quickly and would have a characteristic Doppler shift, which the WOW signal lacked. It wasn't a ground-based transmission reflected off space debris, as no such broadcasts were occurring on that protected frequency. Even natural causes like a cometary outburst were proposed, but the comets suggested weren't in that region of the sky at the time. The signal's properties point to an origin somewhere within our own galaxy, but its ephemeral nature defies a simple answer. We are left with two deeply unsettling possibilities. The first is that we briefly intercepted a one-off, non-repeating transmission from an advanced intelligence, a civilization that sent out a beacon for a short time, or perhaps a powerful, targeted burst meant for another recipient that we simply happened to drift through. The second is that it was an entirely natural astrophysical phenomenon, one so rare and peculiar that we have never observed its like again. The wow signal stands as a monument to both our ambition and our ignorance. It is a tantalizing data point in a universe of noise, a single perfect note played in the cosmic symphony that we heard just once, leaving us forever wondering who or what was the composer. If the Great Attractor represents a cosmic metropolis, a gravitational hub pulling in everything around it, then our next destination is its polar opposite, a sprawling, silent desert of almost nothing. We are venturing into the Boötes void, one of the largest and most perplexing empty spaces in the entire observable universe. Discovered in the 1980s by astronomer Robert Kirshner and his team, this region is not just a simple gap between galaxy clusters. It is a staggering spherical emptiness roughly 330 million light-years across. To grasp that scale, imagine a bubble so vast that if our own Milky Way were placed at its center, the nearest edge of the void would be over 160 million light-years away in every direction. Filling this immense volume with the average density of galaxies we see elsewhere in the cosmos, you would expect to find around 10,000 galaxies within it. Instead, astronomers have only cataloged a few dozen. It is a cosmic ghost town on a scale that defies easy comprehension. This void forces us to confront a fundamental aspect of our universe's structure, the cosmic web. We often think of the cosmos as being uniformly sprinkled with galaxies, but that is an illusion created by our limited perspective. On the very largest scales, the universe is organized into an intricate network, a vast spiderweb of reality. Dense clusters and long, winding filaments of galaxies are interconnected, tracing the underlying distribution of dark matter. These luminous structures are separated by enormous dark voids, and the Boötes void is one of the very largest of these empty chambers. The existence of voids themselves isn't the mystery. It's the sheer mind-boggling size of this one that leaves theorists grappling for explanations. How could a region this vast become so empty? The leading hypothesis points to the very origins of the universe. In the first fleeting moments after the Big Bang, tiny quantum fluctuations were stretched to enormous sizes by a period of rapid inflation. These minute ripples in density became the seeds for all future structure. The densest regions collapsed under their own gravity to form the filaments and clusters we see, while the underdense regions expanded and emptied out over billions of years. For a void as large as Boötes to form, it must have originated from an exceptionally large and underdense region in that primordial soup. Think of it as a valley in the initial topography of the cosmos, a valley so wide that as the universe expanded its hillsides, the surrounding filaments pulled matter away from the center, leaving an ever-growing emptiness. But the void is not completely barren, and its few inhabitants are perhaps the most fascinating part of the story. Scattered across this great emptiness are a handful of isolated, lonely galaxies. These are not like the galaxies we find in crowded clusters. They are often irregular in shape, and their environments are so pristine and quiet that they offer a unique laboratory for studying galaxy evolution in isolation, free from the gravitational harassment and gas-stripping collisions that are common in denser regions. Studying these isolated galaxies can tell us about the bare essentials required for a galaxy to form and survive. The profound emptiness of the Boötes void also has a dramatic effect on the space within it. As the universe continues to expand, the gravitational pull of all the mass in the surrounding filaments actually tugs on the void itself, causing the empty space to expand slightly faster than the universe as a whole. The galaxies inside the void are therefore not only lonely, but are being pushed apart from each other at an accelerated rate, making their isolation even more permanent. The Boötes void stands as a monumental lesson in scale and humility. It reveals that the cosmos is not just a collection of brilliant points of light, but is equally defined by its profound, silent absences. It is a dominant feature in the architecture of reality, a cavern whose sheer size challenges our models of cosmic evolution and reminds us that even nothingness, on a grand enough scale, can be one of the universe's most powerful and puzzling creations. From the immense echoing silence of the Boötes void, we now turn our attention to a structure of intricate and almost artificial beauty, a cosmic jewel box that proves mystery can come in all sizes. Drifting through our own galactic neighborhood, about 2,300 light-years away in the constellation Monoceros, is an object that looks less like a natural formation and more like a piece of abstract art, the Red Rectangle Nebula. When astronomers first observed it, they were so struck by its sharp, geometric appearance that the name was inevitable. Through our telescopes, it doesn't appear as a perfect rectangle, of course, but rather as a vivid, reddish-hued structure with a distinct X-shaped pattern at its core, all enveloped by a series of concentric, ladder-like rungs that give the overall nebula its angular, boxy silhouette. It is a breathtaking sight, a structure that seems to defy the normally chaotic and fluid dynamics of interstellar gas and dust. The secret to this cosmic sculpture lies at its very heart, with a pair of aging stars locked in a tight gravitational embrace. This is a binary system, and the primary star is well on its way to the end of its life. It has exhausted the hydrogen fuel in its core and has swollen into a cool, luminous giant, now in the process of shedding its outer layers into space. This alone would typically create a standard spherical planetary nebula, but the presence of its companion star dramatically alters the outcome. As the giant star sheds its material, the smaller companion star doesn't just watch passively. It orbits through this expelled gas, and its gravity acts like a cosmic egg beater, funneling the material into a dense disk that encircles both stars. This disk is the foundational canvas upon which the red rectangle is painted. Now, with this disk in place, the central giant star begins to blow a fierce wind of particles out from its poles, perpendicular to the plane of the disk. However, because the system is binary, the gravitational tug-of-war between the two stars causes the rotation axis of the giant star to wobble or precess over time. Imagine a spinning top that slowly traces a circle as it spins. This precession means that the two jets of material being ejected from the poles are not firing in straight, steady lines, but are instead tracing out two cone-shaped volumes in space over thousands of years. As these precessing jets slam into the slower-moving gas of the surrounding disk and the interstellar medium, they create shock waves that compress the gas and cause it to glow with that characteristic deep red hue, primarily from a type of emission known as hydrogen alpha light. This is what forms the remarkable X shape we see. It is the hollowed-out double-lobe structure carved by these wobbling jets. But what about the stunning concentric rings, the rungs of the cosmic ladder that make it look so rectangular? This is where the physics becomes even more exquisite and less understood. The prevailing theory suggests that these periodic, evenly spaced shells are the result of pauses in the mass loss process from the central star. Think of it not as a continuous exhale, but as a series of gentle puffs. Every few centuries, the star may have undergone a brief, intense period of mass ejection, followed by a quieter interval. As each successive puff of gas expands outward, it is shaped by the ongoing precession of the jets and the confining influence of the dust disk. The result is a set of expanding, interacting bubbles that, when viewed from our particular vantage point, almost directly along the system's equator, appear as a sequence of sharp, rectangular rungs. The alignment is crucial. If we were to view this system from above its poles, we would likely see a series of concentric rings, a celestial bullseye. Our edge on perspective compresses these rings into the iconic rectangular form. Yet for all the elegance of this model, the red rectangle retains profound secrets. The astonishing symmetry and sharpness of its features are difficult for simulations to perfectly replicate. The precise mechanisms that govern the timing of the mass loss puffs are not entirely clear. Furthermore, the nebula is rich with complex organic molecules known as polycyclic aromatic hydrocarbons, which fluoresce under the harsh ultraviolet light from the hot stellar cores and contribute to the nebula's red color. But their distribution and role in the structure's formation add another layer of chemical complexity. The red rectangle stands as a magnificent example of how the simple, well-understood ingredients of binary stars, stellar winds and gravity, can combine in just the right way to produce a structure of breathtaking complexity. It is a temporary masterpiece, a fleeting stage in the death of a star that offers us a privileged glimpse into the subtle and beautiful physics that can orchestrate chaos into geometry. Now let us shift our perspective from the intricate beauty of a single nebula to a structure of such staggering immensity that it seems to challenge the very foundations of cosmology itself. We are journeying to the farthest reaches of our observable universe, to a region spanning the constellations of Hercules and Corona Borealis, where we find a formation that redefines the word large. This is the Hercules Corona Borealis Great Wall, a colossal filament of galaxies that stretches for an almost incomprehensible 10 billion light years. To even begin to grasp that scale, consider this: the entire span of our observable universe is about 93 billion light years across. This single structure, this one thread in the cosmic tapestry, accounts for more than a tenth of that entire distance. It is not merely a cluster of galaxies, it is a continent of galaxies, a sprawling metropolis of dark matter, gas and stars so vast that its sheer existence sends ripples through our understanding of physics. The discovery of this Great Wall, first identified in 2013 by mapping gamma-ray bursts, presented an immediate and profound challenge to one of cosmology's most cherished principles, the cosmological principle. This principle is a foundational assumption that on sufficiently large scales, the universe is both homogeneous and isotropic. In simpler terms, it means that no matter where you are in the universe, if you zoom out far enough, the cosmos should look roughly the same in all directions, a uniform, evenly distributed soup of matter and energy. This isn't just a philosophical idea, it's the bedrock upon which Einstein's theory of general relativity and our entire model of the Big Bang rests. It's what allows us to make confident predictions about the universe's evolution and its large-scale properties. The Hercules Corona Borealis Great Wall, however, appears to be a glaring exception to this rule. A structure of this magnitude simply should not exist according to our standard models. There is a theoretical upper limit, calculated based on the age of the universe and the influence of dark energy, for how large a gravitationally bound structure can grow. This Great Wall smashes through that limit, suggesting that either our models are incomplete or we are witnessing a statistical fluke of such rarity that it forces us to question our place in the cosmos. This has, of course, ignited a fierce and ongoing debate within the astronomical community. The primary method used to discover the wall, mapping the locations of short-lived gamma-ray bursts, is itself a topic of scrutiny. Gamma-ray bursts are the most violent explosions in the universe, often signaling the death of massive stars or the merger of neutron stars. They are used as brilliant beacons to illuminate the positions of distant galaxies. The argument against the wall's confirmed size hinges on potential observational biases. Could it be that our telescopes are simply better at detecting these bursts in a particular direction, creating an illusion of a concentrated structure? Perhaps intervening cosmic dust or the patchy distribution of galaxies in our local universe is creating a shadow play, a trick of perspective that makes a series of unconnected galaxy clusters appear as one continuous wall. Some astronomers have proposed that what we call the Great Wall might actually be several smaller, unrelated structures that align along our line of sight, their combined profile giving the false impression of a single, unbroken filament. Yet even with these cautions, the evidence for the wall's reality remains compelling for many researchers. Subsequent analyses and different statistical approaches have continued to support the idea that this is a genuine, coherent structure. If it is real, its implications are staggering. It suggests that the seeds of cosmic structure, planted in the inflationary epoch immediately after the Big Bang, were far more varied and potent than we ever imagined. It hints that the mysterious force of dark energy, which drives the accelerated expansion of the universe, may not act uniformly, or that our understanding of gravity itself may need refinement on the largest scales. The existence of the Hercules Corona Borealis Great Wall opens a window into the extreme conditions of the early universe, a time when the initial quantum fluctuations that gave rise to all structure were being imprinted onto the fabric of space-time. This wall could be a fossil from that primordial era, a relic of a time when the universe was far more lumpy and textured than our current models allow. It stands as a monumental question mark etched across the sky, a challenge to our cosmic complacency and a humbling reminder that the universe in its infinite complexity is always capable of surprising us. From the theoretical immensity of the Hercules Corona Borealis Great Wall, we now turn to a spectacle of raw, observable power, a cosmic engine whose portrait made history. Nestled at the heart of the giant elliptical galaxy Messier 87, 55 million light-years away, lies a gravitational monster. This is the supermassive black hole that in 2019 became the first ever to be directly imaged by the Event Horizon Telescope collaboration. That now iconic picture, a fiery ring of light encircling a dark shadow of silence, did more than just confirm a theoretical prediction. It offered humanity a front-row seat to the most extreme physics in the universe. But the black hole itself is only half the story. Emanating from its core is a breathtaking, spear-like jet of superheated plasma, a brilliant lance that stretches for at least 5,000 light-years into the intergalactic void. This jet is not a gentle flow, it is a relativistic beam, a torrent of particles accelerated to over 99% the speed of light, and understanding its origins takes us deep into the complex dance of gravity, magnetism, and matter at the very precipice of oblivion. The journey of this jet begins in the black hole's accretion disk, a swirling, frenzied maelstrom of gas, dust, and shredded stars caught in the black hole's irresistible gravitational pull. As this material spirals inward at velocities approaching light speed, it heats up through friction and compression to temperatures of millions of degrees, causing it to glow with intense radiation across the electromagnetic spectrum. Yet for all this chaos, the material doesn't fall straight in. The black hole is rotating, dragging the very fabric of space-time around with it, an effect known as frame dragging. This rotation twists the inner regions of the accretion disk into a turbulent, magnetized plasma. It is here in this violent, spinning environment that the jet is born. The key ingredient is the magnetic field. As the ionized gas in the accretion disk churns, it amplifies magnetic field lines, winding them up like immensely powerful cosmic springs. Some of these magnetic field lines become anchored in the black hole's rotation itself, and they are flung outward, perpendicular to the disk, forming a tightly collimated, rotating funnel. Now imagine particles from the inner edge of the accretion disk being caught in this magnetic funnel. They don't simply fall into the black hole. Instead, they are slingshotted along these twisting field lines, channeled with unimaginable force away from the black hole's poles. This process, a theoretical model known as the Blandford-Zenagic mechanism, effectively uses the black hole's own rotational energy to power the jet. It transforms the spin of a black hole into a directed, highly efficient particle cannon. The magnetic fields do more than just accelerate the jet. They also act as a straitjacket, preventing the superheated plasma from dissipating into space and keeping it focused into a narrow, coherent beam for thousands of light years. This incredible stability is why we can see the jet from such a vast distance. It is a lighthouse beam cutting through the cosmic dark, powered directly by the spin of a silent, dark giant. This brings us to a fundamental and still unresolved question in astrophysics. Why do some supermassive black holes like the one in M87 produce these magnificent, powerful jets, while others like our own Milky Way's Sagittarius, a star, are relatively quiet and jetless? The answer appears to lie in a combination of factors: spin, magnetic field strength, and the diet of the black hole. A fast-spinning black hole is a prerequisite. It is the reservoir of rotational energy that the magnetic fields can tap into. A dormant, slowly spinning black hole simply lacks the power source, but spin alone is not enough. The black hole also needs a strong, organized magnetic field and a steady, substantial supply of inflowing gas to maintain both the accretion disk and the magnetic flux that threads it. A starving black hole like Sagittarius, a star, which only nibbles on small amounts of gas, cannot build up the necessary magnetic structures to launch a significant jet. Furthermore, the rate and mode of accretion matter. Some black holes accrete matter in a smooth, steady flow, which seems conducive to building stable jets. Others may feed in violent, chaotic bursts, which could disrupt the delicate magnetic architecture needed for jet formation. The orientation of the black hole's spin axis relative to its accretion disk may also play a critical role that we are only beginning to understand. The ongoing research into these cosmic engines is relentless. The Event Horizon Telescope is not resting on its laurels. It continues to observe M87's black hole and others, aiming to create movies that will show the turbulent dynamics of the accretion flow in real time. By watching how the gas moves and how the magnetic field structures change, scientists hope to catch the jet launching process in the act. Simultaneously, observations across other wavelengths, from X-rays that probe the jet's base to radio waves that trace its structure far out into space, are piecing together a more complete picture. Each new data point helps refine the models, bringing us closer to understanding why some of the universe's most massive objects choose to announce their presence with a brilliant, high-energy shout across the cosmos, while others remain in a state of quiet, dark contemplation. But what happens when galaxies don't just drift past one another in the void, but instead engage in a cosmic feast, an act of consumption that forever changes the diner? For a stunning case study, we need to look no further than the giant elliptical galaxy NGC 1316, a behemoth lurking about 60 million light-years away in the southern constellation of Fornax. From a distance, it appears as a classic, smooth and featureless elliptical galaxy, a vast swarm of ancient stars, but peer closer and the serene facade begins to crack, revealing the ghostly fingerprints of a violent and gluttonous past. This galaxy is a known cannibal, and the evidence of its cosmic meals is written across its structure for all to see. The first and most immediate clue is the presence of delicate, intricate dust lanes weaving through its bright core. This is profoundly unusual for an elliptical galaxy, which is typically composed of old, red stars and contains very little of the cold gas and dust needed to form new ones. These dark, swirling ribbons are the shredded remains of a smaller, spiral galaxy that ventured too close. As this spiral was torn apart by NGC 1316's immense gravity, its own rich reservoir of interstellar dust was captured and dragged into the larger galaxy's center. Instead of settling into an orderly disk, this stolen material was chaotically stirred into the existing stellar population, creating the complex, patchy patterns we observe today. It's like finding flecks of pepper in a bowl of vanilla ice cream, a clear sign that something foreign has been mixed in. The second, and perhaps even more telling, piece of evidence comes from its system of globular clusters. Globular clusters are typically dense, spherical collections of hundreds of thousands of very old stars that orbit a galaxy like a swarm of bees. Most large galaxies have them, and they usually exhibit a certain consistency in their color and brightness, reflecting a common, ancient origin. NGC 1316, however, has a globular cluster system that is strangely bimodal. It possesses two distinct populations, one set of faint, red clusters that are native to the galaxy itself, and another more mysterious set of brighter, bluer clusters. These younger, blue clusters are the trophies of its galactic conquests. They were likely stripped from the outer halos of the smaller galaxies it consumed. Some may even have been formed in the violent, compressed shock waves of the collision events themselves, as gas clouds from the merging galaxies smashed together and ignited a firestorm of new star formation. This dual population is a stellar archaeological record, preserving the history of its mergers and the very makeup of its orbiting clusters. This process, where a larger galaxy gravitationally tears apart and assimilates a smaller companion, is what astronomers poetically and accurately term galactic cannibalism. It is the ultimate expression of hierarchical galaxy formation, the dominant theory that suggests the largest galaxies in the universe built themselves up over billions of years through a series of such mergers. NGC 1316 is a prime example of this growth through accretion in action. It didn't start its life as the giant we see today. It has grown to its current size by consuming perhaps several smaller satellite galaxies. Each merger would have been a slow-motion, billion-year-long cataclysm. While individual stars rarely collide due to the vast distances between them, the gravitational tides are immense. They pull and stretch the victim galaxy into long, streaming arcs of stars known as tidal tails, before completely disrupting its structure and swallowing its stars, gas and dark matter. The aftermath of such a feast profoundly reshapes the galaxy's morphology and future. A series of mergers between spiral galaxies, rich in gas, can initially trigger bursts of star formation, but the violent churning of the galactic material eventually randomizes the orbits of the stars. The neat, orderly rotation of a spiral disk is destroyed, leaving behind the chaotic, swarm-like motion of stars that characterizes an elliptical galaxy. The gas that isn't used up in a final starburst is either blown away by powerful winds or funneled to the center, potentially feeding and awakening the supermassive black hole that resides there. This is why giant ellipticals like NGC 1316 are often found at the centers of galaxy clusters. They are the dominant predators in their gravitational domain, having consumed their competitors to become the final, smooth, and quiescent rulers of their cosmic neighborhood. The story of NGC 1316 is a powerful reminder that galaxies are not static islands in the cosmos, but dynamic and evolving entities, their histories of violence and assimilation frozen in the light of their stars. But if we are to truly understand the architecture of galaxies, we must confront the single most dominant, yet completely invisible component of all, the dark matter halo. Picture our Milky Way not just as a brilliant disk of stars, but as a city built within a vast ethereal cloud, a spherical halo of a mysterious substance that extends far beyond the last visible star. This is the invisible elephant in the room, a form of matter that does not emit, absorb, or reflect any form of light, rendering it completely dark to every telescope we have ever built. We cannot see it, touch it, or directly measure it, yet we are more certain of its existence than we are of many things we can see, because its gravitational influence is written into the very motion of the cosmos. The story of its discovery begins not in deep space, but in the careful observations of our own galactic neighborhood. In the 1930s, pioneering astronomer Fritz Zwicky was studying the Coma Cluster, a massive collection of galaxies. By measuring how fast individual galaxies were orbiting the cluster's center, he could calculate the total mass needed to keep them gravitationally bound. The result was staggering. The mass required was hundreds of times greater than the mass of all the visible stars, gas, and dust combined. He called this missing mass Dunkel Materie, or dark matter, and while his work was largely ignored for decades, the evidence has since become overwhelming and inescapable. The most compelling proof comes from the rotation curves of spiral galaxies. According to the laws of gravity, stars and gas on the outer edges of a galaxy, far from the central mass, should orbit much more slowly, just as Pluto orbits the Sun far more sluggishly than Mercury. Yet when astronomers like Vera Rubin measured these orbital speeds in the 1970s, they found something astonishing. The velocities of stars and gas clouds remained high, flatlining all the way to the visible edge of the galaxy and beyond. This meant that the gravitational pull holding these fast-moving outer stars in their orbits was coming from somewhere other than the luminous matter we could see. There had to be a massive unseen halo of matter enveloping the galaxy, its gravitational reach extending far into the void. This dark matter halo is not a minor component. It is the foundational skeleton upon which the entire visible galaxy is built. In the early universe, slight overdensities of dark matter, governed by its own gravity, began to collapse first, forming gravitational wells. Ordinary matter, the protons, neutrons, and electrons that make up everything we see, was then drawn into these wells. But while dark matter interacts only through gravity, ordinary matter can also collide, radiate away energy, and slow down. This allowed the normal matter to settle into the dense, rotating disks we recognize as spiral galaxies, while the dark matter, unable to shed its energy, remained in a vast, puffy, and roughly spherical halo, its particles on wide, looping orbits that never condense. Without this dark matter scaffolding, there simply wouldn't have been enough gravitational glue to collect the gas needed to form the first stars and galaxies. The universe would be a much darker, more diffuse place. The nature of this mysterious substance, however, remains one of the greatest enigmas in all of science. We know what it is not. It is not made of atoms. It is not the planets, asteroids, or cold gas we haven't found yet. It is not black holes in any significant quantity. The leading theoretical candidate is a class of particles known as WIMP, or weakly interacting massive particles. These hypothetical particles would be heavy, move relatively slowly, and interact with normal matter only through gravity and perhaps the weak nuclear force, making them incredibly difficult to detect. For decades, physicists have built exquisitely sensitive experiments deep underground, in old mines and tunnels, shielded from cosmic rays, hoping to catch the rare, faint ping of a WIMP colliding with an atomic nucleus. So far, these direct detection efforts have yielded no confirmed signal. This lack of discovery has fueled alternative ideas. Another prominent candidate is the action, an extremely light particle born out of theories attempting to solve a different problem in particle physics. Actions would behave more like a pervasive cosmic field, and dedicated experiments are now searching for their subtle conversion into photons in powerful magnetic fields. There are even more radical proposals, such as the idea that our understanding of gravity itself is flawed on galactic scales, a theory known as modified Newtonian dynamics, or MEND. This theory suggests that at very low accelerations, like those experienced at the fringes of galaxies, gravity behaves differently than Newton or Einstein predicted, eliminating the need for dark matter altogether. While one can explain some galactic rotation curves, it struggles to account for the wealth of other evidence, such as the way massive galaxy clusters bend the light from objects behind them, an effect called gravitational lensing, which clearly points to the presence of vast amounts of unseen mass. The true identity of dark matter is more than just a puzzle. It is the key to unlocking the ultimate fate of the cosmos. This invisible halo governs not just the life of a single galaxy, but the evolution of the entire cosmic web. Its gravitational pull dictates the rate at which galaxies form and cluster together, and its amount and properties determine whether the universe will expand forever or eventually collapse back on itself. We're like sailors on an ocean, feeling the powerful tug of a deep, unseen current, knowing that our journey and destination are entirely dependent on a force we have yet to fully comprehend. While our own galaxy's history is written in the ghostly bubbles at its core, the story of its ongoing growth and influence is dramatically illustrated by a sprawling, ethereal river of gas flowing across the southern sky. This is the Magellanic Stream, a colossal ribbon of neutral hydrogen that arcs for over 500,000 light-years, a length that would span the entire distance from our Milky Way to the Andromeda Galaxy and beyond. To the naked eye, it is completely invisible, but to radio telescopes, it paints a breathtaking picture, a delicate filamentary trail of cosmic debris flowing behind the two most prominent dwarf galaxies orbiting our own, the Large and Small Magellanic Clouds. For a long time, this stream was a profound puzzle. How could two such small galaxies produce such an immense trailing wake? The answer lies in a gravitational drama playing out over billions of years, a real-time demonstration of how large galaxies cannibalize their smaller neighbors. The leading theory for its formation is a powerful combination of two destructive forces. The first and most persistent is the relentless gravitational pull of the Milky Way. As the Magellanic Clouds orbit our galaxy, they don't travel through empty space, they move through the Milky Way's extended dark matter halo. The force of gravity is not uniform. The side of the clouds closer to our galaxy feels a stronger pull than the side farther away. This difference, known as a tidal force, acts like a cosmic stretching machine, gradually pulling gas and even stars away from the dwarf galaxies. Over many orbits, this process has stripped away vast quantities of gas, flinging it into a long, trailing orbit that mirrors the path of the clouds themselves. It's similar to the way the moon's gravity creates tides on Earth, but on a galactic scale, the result is not a gentle rise and fall of water, but the violent and permanent stripping of an entire galaxy's gaseous reservoir. However, tides alone may not tell the whole story. There is compelling evidence that the Magellanic Clouds have not always been separate entities peacefully orbiting the Milky Way. Observations of their structure and motion suggest that they are a bound pair, orbiting each other, and that they likely had a close encounter or even a direct collision hundreds of millions of years ago. This violent interaction would have been catastrophic, violently stirring up their interstellar gas and flinging huge amounts of it into intergalactic space. Once this gas was dislodged and set adrift, it became easy prey for the Milky Way's tidal forces, which then shaped and stretched it into the long, coherent stream we observe today. So the Magellanic Stream is likely the product of a 1-2 punch, an initial galactic collision that loosened the gas, followed by billions of years of tidal stripping that sculpted it into its current form. This makes it a fossil record of not just one, but two types of galactic interaction preserved in the faint glow of hydrogen gas. The significance of this cosmic ribbon extends far beyond its spectacular appearance. It provides astronomers with a rare and valuable laboratory for studying the life cycle of galaxies. Dwarf galaxies like the Magellanic Clouds are the building blocks of larger galaxies like our own, and the stream is a live-action replay of the accretion process that built the Milky Way's halo over cosmic time. By studying the composition and dynamics of the gas in the stream, we can learn what kind of material is being fed into our galaxy. This is crucial because gas is the raw fuel for star formation. The Magellanic Stream is in effect a pipeline delivering pristine hydrogen to the Milky Way's doorstep, yet recent observations have revealed a surprising twist. As this gas approaches our galaxy, it seems to be interacting with the Milky Way's own extended corona of hot ionized gas. This collision creates a shock front, much like the bow wave of a ship, which may be heating and dispersing the incoming stream, potentially making it more difficult for the gas to cool down and eventually form new stars. This interaction gives us a front row seat to the complex physics of gas accretion, showing that the journey from intergalactic space to a star-forming cloud is a turbulent and perilous one. The Magellanic Stream is more than just a beautiful relic. It is a dynamic and evolving structure, a key piece in the puzzle of how galaxies gather their resources and how they continue to grow and change by consuming the smaller cosmic structures that orbit them. Journey far beyond the serene beauty of Hoag's object to an era when the universe was in its tumultuous youth, and you will find a celestial spectacle of pure, unadulterated violence. At an astonishing distance of 11 billion light-years away, the galaxy R5519, dubbed the Ring of Fire, presents a vision of cosmic chaos frozen in time. We see it not as it is today, but as it was just 3 billion years after the Big Bang, a period of frantic galaxy formation and frequent catastrophic collisions. And what we see is breathtaking, a colossal, blazing ring of intense star formation, a perfect circle of brilliant blue newborn stars surrounding a conspicuously empty and dark central hole. While its circular form might echo the tranquil perfection of Hoag's object, its origin story could not be more different. This is not a galaxy of serene, resonant formation. This is a galaxy that has survived a cosmic bullet to the heart. The leading theory explaining this magnificent structure is one of extreme violence, a head-on galactic collision of almost unimaginable precision. Imagine a quiet, orderly spiral galaxy, much like our own Milky Way, rotating peacefully in the early universe. Then another smaller galaxy, perhaps a compact dwarf, comes hurtling through space on a near-perfect trajectory, not a glancing blow but a direct hit, piercing the very center of the spiral's disk like a celestial spear. This isn't a slow gravitational dance of merger. This is a high-speed, catastrophic puncture. The intruder galaxy would have passed straight through the disk and continued on its way, its gravity drastically and suddenly altering the structure of the larger galaxy it left behind. The key to the ring's formation lies in what happens next. The immense gravitational shock of this central impact sends a powerful wave of compression racing outward through the galactic disk, like the ripples from a stone dropped in a pond, but on a scale of thousands of light years. This is known as a density wave. As this wave propagates outward, it sweeps up the vast reservoirs of gas and dust that fill the interstellar medium, compressing them to incredible densities. In the wake of this wave, the conditions become perfect for the ignition of new stars. The compressed gas clouds collapse under their own gravity, lighting up in a firestorm of stellar birth that traces the exact circular path of the expanding shockwave. This creates the brilliant blue ring. We observe a direct map of the collision's aftermath. What makes our 5519 so exceptionally important is the timing of this event and the clarity of the snapshot it provides. In the local modern universe, we see ring galaxies like the Cartwheel Galaxy, which confirm this collision model. But finding such a pristine example, 11 billion light years away, is like discovering a fossil of the very first predators on Earth. It tells us that these violent, transformative processes were not rare in the early cosmos. They were a fundamental and frequent mechanism for galaxy evolution and star formation during the universe's most active period. The sheer size of the ring is another clue to the violence of its birth. The diameter of the star-forming ring in our 5519 is massive, significantly larger than that of our own Milky Way. This scale suggests the initial impact was extraordinarily energetic, launching the density wave outward with tremendous force. Furthermore, the central hole is not completely empty. It does contain some older, redder stars, the surviving population from the original galactic core. But the collision has effectively shut down star formation in the central region, either by violently ejecting the gas or by heating it to such an extent that it can no longer collapse to form new stars. The galaxy's core has been left a ghost town, while its outskirts blaze with the light of stellar youth. This discovery challenges our understanding of how quickly such intricate structures could form after the Big Bang. For a galaxy to have already evolved into a stable disk, only to then be rearranged into a perfect ring by a collision, all within the first 3 billion years of the universe, speaks to an era of incredible dynamicism and chaos. It provides direct evidence that the hierarchical model of galaxy formation, where large galaxies grow through a series of mergers and acquisitions, was not always a slow process. In the dense early universe, these high-speed, violent encounters were a primary driver of morphological change, capable of creating some of the most striking and beautiful structures we can observe. The Ring of Fire galaxy, therefore, is more than just a pretty picture. It is a forensic snapshot from a crime scene on a galactic scale, a brilliant and brutal reminder that the cosmos has always been a place of both creation and destruction, often two sides of the very same coin. Now consider a different kind of galactic interaction, one not of stellar cannibalism but of a prodigal son returning home. High above the plane of our Milky Way, a cosmic phantom is hurtling toward us, a colossal and mysterious structure known as the Smith Cloud. Discovered in the 1960s by astronomy student Gail Smith, this is no ordinary cloud of gas. It is a gigantic, high-velocity cloud of neutral hydrogen, a river of primordial fuel stretching 11,000 light-years long and 2,500 light-years wide. If our eyes could see its faint radio glow, it would appear as large as 30 full moons across the night sky, but its most defining characteristic is its motion. This immense cloud is not drifting aimlessly. It is on a direct collision course with the galactic disk of the Milky Way, plummeting toward us at nearly 200 miles per second. In approximately 30 million years, it will slam directly into the spiral arm of our galaxy, an event that promises to be both destructive and creatively spectacular. What makes the Smith Cloud so particularly fascinating to astronomers is not just its trajectory, but its surprising composition. For a long time, it was assumed that such high-velocity clouds were pristine, left over from the formation of the universe and composed almost entirely of hydrogen and helium, the original elements forged in the Big Bang. These will be visitors from the intergalactic void, falling into our galaxy for the first time. However, when scientists used the Hubble Space Telescope to analyze the light from distant quasars shining through the Smith Cloud, they made a startling discovery. The cloud's gas is polluted. It contains significant amounts of sulfur, oxygen, and other heavy elements, in abundances similar to what we find in the outer regions of our own sun. This chemical fingerprint is a cosmic barcode, and it tells a very different story. The Smith Cloud is not a pristine visitor, it is a native. It originated from within the Milky Way itself, and it is now in the process of falling back home. This revelation immediately raises a compelling question. What tremendous force could have blasted a cloud of gas this massive clear out of our own galaxy? The leading theory points to a cataclysmic event millions of years ago, likely a powerful supernova explosion or even a chain reaction of supernova in a region of intense star formation. Picture a stellar nursery, a dense nebula where massive stars are born, live fast and die young. When these stars reached the end of their lives, they exploded with unimaginable force. In some scenarios, if these explosions occurred in a coordinated fashion, their combined energy could have been focused enough to act like a cosmic cannon, punching a titanic bubble of gas right through the galactic disk and ejecting it high into the halo. The Smith Cloud is the surviving fragment of that ejected material, a piece of our galaxy that was violently launched into space and is now pulled by the Milky Way's relentless gravity, making its return journey. Another more exotic possibility involves an interaction with the dark matter halo. Perhaps the cloud was once a small, gas-rich dwarf galaxy that ventured too close to the Milky Way. Our galaxy's gravity could have stripped away all of its stars, which are more tightly bound, while easily tearing away its vast, diffuse envelope of gas. This would leave behind a pure gas cloud, now enriched with the heavy elements that dwarf galaxy stars had produced. While the chemical evidence strongly favors the galactic fountain model of supernova ejection, The true origin remains an active area of investigation. The impending collision is not a threat to existing stars, as the cloud is incredibly diffuse. Its average density is less than 1 atom per cubic centimeter, a vacuum far emptier than anything we can create on Earth. The real drama will unfold in the interstellar medium, when this massive blob of relatively cool, dense gas smashes into the much hotter, thinner gas of our galaxy's spiral arm. It will create immense shock waves. These shock fronts will race through the cloud, compressing the hydrogen gas violently and triggering a cascade of gravitational collapse within countless localized pockets. Each of these collapsing knots of gas will heat up, and when the core temperature and pressure become high enough, nuclear fusion will ignite. In essence, the Smith cloud's impact will serve as the ultimate trigger for a magnificent stellar baby boom, a fireworks display of star formation that could light up an entire section of the galactic disk with the brilliant blue light of millions of new stars. This process of galactic recycling is a fundamental part of a galaxy's life cycle. The Smith cloud is a dramatic example of how galaxies can expel material through violent events, only to reaccrete it later to fuel future generations of stars. It is a celestial return on investment, a delivery of processed materials that will one day be incorporated into new solar systems and perhaps new worlds. This cloud, a ghost from our galaxy's own violent past, is destined to become the cradle for its future. For generations, schoolchildren have drawn the Milky Way as a simple, elegant pinwheel, a graceful swirl of stars with arms spiraling out from a bright central hub. It's an image deeply embedded in our collective consciousness, but what if that iconic image is fundamentally wrong? The truth is, our galaxy is not that classic spiral. It is a cosmic hybrid, a barred spiral galaxy. At its heart lies a colossal, rigid structure, a dense, elongated bar composed of billions of stars, stretching for thousands of light years. Picture not a round hub, but a gigantic stellar football with the familiar spiral arms not emerging from a center point, but streaming away from the ends of this central bar. This isn't a minor detail, it's a fundamental reshaping of our galactic home, and its influence over the entire galaxy is profound and relentless. This galactic bar isn't a static, decorative feature. It is a dynamic, rotating engine, and its gravitational influence orchestrates the motion of stars and gas across vast stretches of the Milky Way. The bar's immense gravity creates a powerful, non-circular force field. As stars and giant clouds of gas orbit the galactic center, their paths are not simple circles. Instead, they get caught in the bar's gravitational wake, funneled along specific streams and trajectories. Think of it as a colossal, slow-motion blender stirring the inner galaxy. This gravitational steering has a direct and dramatic consequence. It acts as a cosmic fuel pipeline, channeling immense amounts of interstellar gas inward toward the galactic center. The gas doesn't fall straight in. It follows chaotic, elliptical orbits, losing energy through collisions and shock waves as it is driven relentlessly toward the core. This constant influx of fresh material has monumental implications. It can trigger intense, episodic bursts of star formation in the central regions, creating the dense stellar clusters we observe there. More ominously, this river of gas flows directly toward the supermassive black hole, Sagittarius, a star that resides at the very center. The bar, therefore, may be the primary mechanism that periodically awakens this sleeping giant, feeding it just enough material to cause the kind of outburst that could have created structures like the Fermi Bubbles we discussed earlier. Our galaxy's central bar is not just a shape, it is the master regulator of the galactic core's activity, a pump that controls the lifeblood of the inner Milky Way. Yet for something so fundamental to our galaxy's structure and evolution, determining its precise characteristics has proven to be one of the most stubborn challenges in modern astronomy. The primary obstacle is our own vantage point. We are not outside observers looking down on the Milky Way. We are embedded within its disk, about halfway out from the center. Our view toward the galactic core is completely obscured by thick clouds of interstellar dust that block visible light. It's like trying to map the shape of a forest while standing in the middle of it, surrounded by a dense, perpetual fog. To pierce this veil, astronomers must rely on longer wavelengths of light that can penetrate the dust, such as infrared and radio waves. But even with these tools, the task is immensely complex. Different observational techniques have yielded surprisingly different results. Some studies which track the motions and distributions of old red giant stars suggest a relatively shorter and fatter bar. Others, focusing on the intense infrared light from younger stars, point toward a longer, thinner structure. The estimates for its length vary widely, from around 5,000 to 15,000 light years. Similarly, its orientation relative to our solar system is a matter of intense debate. Is it tilted at a 30, 45, or even 60-degree angle to the line between us and the center? Each new survey seems to add another piece to the puzzle, but the complete picture remains frustratingly out of focus. The quest to map the bar is more than an academic exercise in galactic cartography. Its true size, shape, and rotation speed are critical parameters that influence nearly every model of the Milky Way's dynamics and history. The bar's gravitational field dictates the orbits of stars not just in the center, but far into the disk, creating resonances that can either shepherd stars into the spiral arms or scatter them into the halo. Its rotation speed determines how effectively it can funnel gas inward, which in turn regulates the growth of the central black hole and the rate of star formation in the nuclear region. Unlocking the precise nature of our galaxy's bar is the key to understanding the Milky Way's past, present, and future evolution. It represents a humbling reminder that even as we map the farthest reaches of the cosmos, some of the most profound and fundamental mysteries are still right here at home, hidden in plain sight at the very heart of our own galactic city. Yet for all the violent collisions and swirling bars we find in the cosmos, some of the most profound mysteries are not solid objects at all, but rather ethereal, glowing giants from the dawn of time. Imagine a cloud of gas so vast it could swallow our entire local group of galaxies, a cosmic ghost glowing with a faint, otherworldly light. These are the Lyman alpha blobs, and they are some of the largest individual structures ever identified in the universe. Discovered in the deep fields of our most powerful telescopes, these colossal entities are immense clouds of pristine hydrogen gas, some stretching for hundreds of thousands of light years across. They are named for the specific type of light they emit, a particular wavelength of ultraviolet radiation released when electrons within hydrogen atoms drop to their lowest energy state. In the modern local universe, seeing a cloud of hydrogen glow this way wouldn't be especially unusual, but the sheer scale and brilliance of these ancient blobs, observed when the universe was only a few billion years old, presents a monumental puzzle. How could something so diffuse shine so brightly, and what cosmic engine could possibly power such a faint yet gigantic beacon? The search for the power source behind these luminous leviathans leads us down several fascinating and competing paths. One of the most straightforward theories points to an era of frantic, explosive star formation happening deep within the cloud. In this scenario, the blob is actually a vast stellar nursery, a cradle for the birth of entire galaxies. Within its murky depths, millions of massive, hot young stars are igniting all at once. These stars flood the surrounding hydrogen gas with an intense torrent of ultraviolet radiation, which energizes the atoms and causes them to re-emit that energy as the characteristic Lyman alpha glow. The immense size of the blob would then be a testament to the sheer volume of gas available for this process, a single connected region where galaxy formation is occurring on a staggering scale. However, for some of the largest and brightest blobs, the energy required is so prodigious that even a frenzy of star formation struggles to account for it all, pushing astronomers to consider even more powerful cosmic engines. This leads to a second, more violent hypothesis: the presence of voracious supermassive black holes. At the heart of many of these blobs, astronomers often find the brilliant, pinpoint light of quasars or other active galactic nuclei. As these black holes accrete vast amounts of gas, the material heats to millions of degrees in the surrounding disk, blasting out tremendous amounts of energy across the electromagnetic spectrum. This intense radiation, far more powerful than starlight alone, could be what is illuminating the entire surrounding cloud of hydrogen, making it glow from the inside out. The blob in this case is the visible manifestation of a black hole's sphere of influence, a marker of the incredible power these dark giants can wield over their environment, lighting up volumes of space larger than any single galaxy. A third and perhaps most profound theory suggests the power comes from the very architecture of the cosmos. The Lyman alpha blob might not be powered by a central engine at all, but could instead be a natural consequence of the cosmic web in action. In this model, the blob marks a critical intersection point in the web, a gravitational knot where vast, cold rivers of primordial gas are flowing in from intergalactic space and funneling directly into the waiting arms of a forming galaxy cluster. As this cold gas streams along the dark matter filaments and crashes together at the nexus, the sheer gravitational energy of the infill is converted into heat and light. The resulting shock waves could be what excites the hydrogen, causing the entire vast reservoir of incoming fuel to glow with Lyman alpha light as it settles into the potential well. Here, the blob is not a site of creation or destruction, but one of cosmic assembly, a visible signpost of the universe actively building its largest structures, its glow emanating from the gravitational birth pangs of a future cluster of galaxies. The true nature of these enigmatic structures likely involves a combination of these processes. They may represent a brief hyperactive phase in the life of a protocluster, where cold gas accretion, frantic star formation, and feeding black holes are all happening simultaneously, their combined energies lighting up the cosmic dawn. Each blob is a unique laboratory, a snapshot of the universe at its most dynamically fertile, challenging us to decipher the complex interplay of forces that shape the first great structures in the cosmos. Their faint, widespread glow is a direct message from a time of tumultuous creation, a reminder that the empty spaces between galaxies are not so empty after all, but were once filled with the brilliant, swirling potential of everything to come. But even as we chart the ghosts of our galaxy's past and the streams of its present, we are locked in a gravitational dance with a future that is both certain and spectacular. For decades, we viewed the Andromeda Galaxy as a distant, fuzzy neighbor, a spiral island slowly circling our own in the local group. Then in 2012, data from the Hubble Space Telescope delivered a startling revelation. Andromeda is not just circling, it is heading straight for us. Our two galaxies are on an inevitable collision course, a slow-motion cosmic car crash set to unfold over the next several billion years. This isn't a possibility or a theory. By precisely measuring the sideways motion of Andromeda, scientists have confirmed that the mutual pull of gravity between our galaxies has overcome the expansion of the universe, sealing our fates. The coming merger will be the most transformative event in the entire future history of our solar system, a billion-year-long ballet that will utterly reshape the night sky and forge a new galactic home. The first act of this epic will begin in approximately 4.5 billion years. Andromeda, which currently appears as a small, faint smudge, will grow larger and larger in our sky, eventually spanning the entire dome of the night. It will no longer be a distant object, but a looming presence. As the galaxies make their first close pass, they will not slam directly into one another. Instead, they will swing past each other like two vast flocks of birds grazing one another's edges. This initial encounter will be a gravitational catastrophe. The delicate spiral structures of both the Milky Way and Andromeda will be shredded. Their mutual gravity will pull long, streaming tails of stars, gas, and dust out into intergalactic space, creating brilliant, arcing bridges of light between them. Within the galaxies themselves, the orderly rotation of stars will be thrown into chaos. The gravitational tides will compress giant clouds of interstellar gas, triggering a firestorm of new star formation. The sky would be filled with the blazing light of millions of newborn stars, and the rate of supernova explosions would skyrocket, making the cosmos a far more violent and radiant place. After this first disruptive pass, the two galaxies, now permanently damaged and entwined, will swing apart, only to be pulled back together by their unrelenting gravity. They will fall back toward each other for a second, closer encounter, and then a third, their orbits decaying with each pass. Over the next 1 to 2 billion years, they will engage in a series of ever tighter loops, a cosmic dance of death and rebirth. With each close approach, more and more of their original structure is stripped away, and their stars are thrown into increasingly random orbits. This is the key to understanding the final outcome. A spiral galaxy's beauty comes from the ordered circular motion of its stars within a thin disk. The violent gravitational perturbations of the merger act like a giant mixer, randomizing those orbits and erasing the disk entirely. The stars are flung into a much larger, three-dimensional swarm. The final act will see the two cores of the galaxies, each harboring a supermassive black hole, merge into one. After perhaps 7 or 8 billion years from today, the chaotic dance will cease and a new, stable galaxy will be born. This will not be a spiral galaxy. All the beautiful pinwheel structures will be gone, replaced by the smooth, featureless glow of a giant elliptical galaxy. Astronomers have already given this future entity a name, Milkdromda. It will be a vast, redder galaxy, dominated by older stars, with most of its gas having been either used up in the frenzy of star formation or blown away by the relentless supernova winds. The era of prolific star birth will be over, and Milkdromda will enter a long, quiet autumn. Throughout this entire cosmic upheaval, there's one profoundly reassuring fact: the stars themselves are incredibly unlikely to collide. A galaxy is, for the most part, empty space. The average distance between stars is so immense that if you scaled the sun down to the size of a marble, the nearest star would be over 4,000 miles away. While the galaxies will pass through each other, the stars within them are like two swarms of gnats flying through one another. The individual gnats will almost never touch. Our solar system will almost certainly survive intact. However, its place within the new galaxy will be radically different. The gravitational tides will likely fling us out into the outer halo of Milkdromda on a new, wildly elliptical orbit far from the bright core. From this new vantage point, the night sky will be unrecognizable. The familiar band of the Milky Way will be gone, replaced by a uniform, spheroidal distribution of stars with no discernible structure. The Andromeda Galaxy as a separate entity would no longer exist. We will be citizens of a completely new cosmos, looking out at a sky that tells the story of a colossal merger, billions of years in the making, a permanent monument to the dynamic, ever-changing nature of the universe on the grandest of scales. As we witness the grand, slow-motion dance of galactic collisions, it's crucial to remember that galaxies are not passive islands. They are dynamic systems with their own powerful internal engines, capable of erupting with violence that can shape their own destiny. A stunning example of this self-sculpting power can be found in the spiral galaxy NGC 3079, located about 67 million light-years away. Here, astronomers have observed a spectacular and furious event, a pair of colossal bubbles of superheated gas erupting from the galactic core and stretching for an astonishing 50,000 light-years above and below the disk. These are not gentle, slow-expanding shells. They are titanic, energetic outflows, so immense and violent they have earned the fitting name, galactic geysers. The sheer force required to launch such gigantic structures directly implicates the galaxy's central supermassive black hole. Similar to the engine in M87, the black hole at the heart of NGC 3079 is a powerful dynamo. As it feeds on surrounding gas, it doesn't just glow brightly, it can launch jets of plasma and radiation. However, in the case of NGC 3079, the story is more complex. Observations reveal that these geysers are not solely the product of a black hole jet. Instead, they are the result of a powerful, combined effort. The central region of this galaxy is also undergoing a ferocious burst of star formation, a so-called starburst. This means millions of stars are being born in a relatively small volume of space. These massive young stars live fast and die young, exploding as supernova in rapid succession. The combined effect is a hurricane of stellar winds and shock waves, pumping enormous energy into the surrounding interstellar medium. It is the synergy of these two phenomenal power sources, the black hole's activity and the starburst's fury, that creates the unique and overwhelming force behind the geysers. The outflows are essentially a superheated, multi-million-degree plasma, detected by their intense X-ray emission, which is being violently blown out of the galaxy's disk, punching its way through the halo. This incredible eruption is far more than just a cosmic light show. It represents a critical feedback mechanism that governs the entire life cycle of the galaxy. This process, known as galactic feedback, is a fundamental regulatory system. On one hand, gravity works tirelessly to pull gas inward, fueling both the central black hole and the formation of new stars. But if this process continued unchecked, the galaxy would rapidly consume all its available fuel in a short, violent burst, leaving it a quiescent, red and dead elliptical. The geysers are the universe's built-in thermostat. By violently ejecting huge quantities of gas out of the galaxy, they effectively shut down the very processes that created them. The outflows remove the raw material for future star formation, quenching the starburst. Simultaneously, by blowing gas away from the galactic center, they starve the supermassive black hole, limiting its growth and calming its activity. This self-regulation ensures that the galaxy evolves in a controlled manner, preventing it from burning through its fuel reserve too quickly and allowing for a more sustained, long-term evolution. The dramatic structures in NGC 3079 invite a direct comparison to the Fermi bubbles in our own Milky Way. Both are pairs of colossal, bipolar bubbles emanating from a galactic center, and both are evidence of a powerful, explosive event in the galaxy's recent past. Yet the differences between them are as revealing as their similarities. Our Fermi bubbles are much more subtle, detected primarily in high-energy gamma rays and radio waves, and they are significantly cooler and less energetic than the violent, X-ray bright geysers of NGC 3079. This suggests that the eruption that created our bubbles was a quieter, perhaps more isolated event, likely driven by a past outburst of our own supermassive black hole, Sagittarius, a star, without the accompanying widespread starburst happening in NGC 3079. Our galaxy's event was a powerful shout, while the event in NGC 3079 is a continuous, raging scream. This comparison is profoundly instructive. It shows us that galactic feedback is a universal process, but its intensity and character vary dramatically from galaxy to galaxy, depending on the specific balance of power between its central black hole and its star-forming regions. Studying these galactic geysers gives us a front-row seat to one of the most extreme versions of this feedback loop in action, a vivid demonstration of how galaxies can act as their own architects, using their most violent internal forces to carve out their own future and determine their ultimate fate. After witnessing the furious galactic geysers sculpting a galaxy from within, we now turn to a cosmic entity of an entirely different nature, one defined not by what blazes with light, but by what lingers in profound shadow. Drifting through the distant Coma cluster, some 330 million light-years away, is a ghost. Its official designation is Dragonfly 44, but it might as well be called the Dark Galaxy. It is a celestial paradox of staggering proportions. By all measures of its gravitational influence, Dragonfly 44 is a giant, a galaxy nearly as massive as our own Milky Way. Yet if you were to point a telescope at it, you would see almost nothing. It is a wisp, a faint smudge of light so diffuse that it was only discovered in 2015, thanks to a specially designed telescope that could detect such incredibly low-surface brightness objects. This is the core of the mystery, a galaxy with the weight of a titan, but the faint glow of a dwarf. The numbers behind Dragonfly 44 are what truly cement its status as a profound cosmic anomaly. To have the gravitational heft of the Milky Way, a galaxy must contain the mass of about 1 trillion suns. Our Milky Way, with its hundreds of billions of stars, fits this profile. But Dragonfly 44 is different. It emits only about 1% of the light we would expect from an object of its immense mass. The rest of its substance, a staggering 99.99%, is not just missing, but invisible. It is made of dark matter. This means the visible component of this galaxy, the stars, gas, and dust we can actually see, is a mere sprinkling, a fleeting afterthought clinging to an immense, unseen mountain of dark matter. The stars in Dragonfly 44 are not packed into a dense disk or bulge. They are scattered across a vast volume, forming an ultra-diffuse galaxy. It's as if you took all the stars of the Milky Way and spread them out across a region 10 times wider. The resulting dim, ethereal cloud would be what we see as Dragonfly 44, a galaxy that is all halo and almost no heart. The existence of such a dark matter-dominated galaxy forces us to confront a fundamental and unsettling question about how galaxies are born. In our standard model of cosmology, galaxies form when vast halos of dark matter collapse under their own gravity, creating gravitational wells that then attract ordinary, baryonic matter, the gas that cools, condenses, and eventually forms stars. The dark matter is the framework, and the visible stars are the luminous finish. Dragonfly 44 challenges this symbiotic relationship. It possesses one of the most massive dark matter halos we have ever measured, a framework built for a brilliant metropolis of stars. Yet that metropolis was never constructed. For reasons we do not yet understand, the process of converting gas into stars failed spectacularly here. One compelling theory points to the galaxy's environment. Dragonfly 44 resides in the crowded, violent Coma cluster, a gravitational maelstrom of thousands of galaxies. Early in its history, as it moved through the cluster, it may have had its primordial gas reservoir violently stripped away by the intense pressure of the intergalactic medium, a process known as ram pressure stripping. Imagine a galaxy sailing through a cosmic headwind so powerful that it blows away all the loose gas, the very fuel for future stars, leaving only the dark matter halo and the stars that had already formed intact. Another possibility is that the galaxy experienced a series of intense supernova explosions early on, which blew out the remaining gas before it could form many more stars. In either case, the result is the same, a galaxy that built a magnificent dark matter skeleton, but never grew a luminous body. This makes Dragonfly 44 far more than just a cosmic curiosity. It is a critical natural experiment. By studying it in other ultra-diffuse galaxies, we can effectively isolate the properties and behavior of dark matter in a way that is impossible in a galaxy like our own, where the visible and dark matter are deeply intertwined. The motion of its sparse star clusters and individual stars serves as a direct tracer for the shape and density of the underlying dark matter halo. These observations are already providing crucial clues, suggesting the halo of Dragonfly 44 is remarkably similar in size and structure to that of the Milky Way, further highlighting the stark disparity in stellar content. This ghostly galaxy presents a stark alternative pathway for galactic evolution, proving that a massive dark matter halo does not guarantee a brilliant galaxy. It raises the possibility that such dark galaxies could be incredibly common, perhaps even outnumbering the luminous ones, floating unseen throughout the universe. Their silent, massive presence a permanent reminder of how much we have yet to learn about the invisible forces that truly shape the cosmos. Now let us examine a celestial object that looks less like a galaxy and more like a perfect splash frozen in the cosmos. 500 million light-years away in the constellation Sculptor lies the Cartwheel Galaxy, a breathtaking example of a ring galaxy and perhaps the most iconic illustration of a galactic bullseye collision in the entire universe. Its appearance is immediately arresting. At its core, you see a brilliant, compact hub of older, yellowish stars. Surrounding this is a stark, dark gap, a region of relative emptiness. Beyond this gap blazes the galaxy's most famous feature, a colossal, luminous ring of intense blue light, a perfect circle of furious star formation that forms the galaxy's primary disk. Connecting this vibrant outer ring to the inner core are faint, wispy structures that look like the spokes of a wheel, giving the galaxy its evocative name and completing a picture of cosmic symmetry born from pure chaos. This magnificent structure is not the result of serene, internal processes, but rather the aftermath of a catastrophic and incredibly precise intergalactic event. The prevailing scenario, supported by sophisticated computer simulations, is one of a high-speed, head-on collision. Imagine a quiet, orderly spiral galaxy, much like our own Milky Way, rotating peacefully. Then a smaller, intruder galaxy, perhaps one-third its size, comes hurtling through space on a near-perfect trajectory, not a glancing blow, but a direct hit, piercing the larger galaxy's disk straight through its center. Think of it as a celestial bullet fired through a spinning pinwheel. The intruder did not merge with the larger galaxy. It punched straight through and continued on its journey, its gravity acting as a colossal tuning fork that sent a powerful, symmetrical shockwave rippling outward through the larger galaxy's disk. This outgoing shockwave is the key to the entire spectacular phenomenon. As this wave of immense pressure expanded at supersonic speeds, it swept up the vast reservoirs of hydrogen gas that were scattered throughout the galactic disk. Just as a snowplow collects snow into a growing pile ahead of it, the shockwave compressed this diffuse gas into an incredibly dense, narrow ring. Within this compressed wall of gas, the conditions became perfect for a firestorm of star birth. The gravitational collapse of these dense gas clouds ignited millions of new, massive, and incredibly hot stars all at once. These brilliant, blue, short-lived stars are what make the outer ring shine with such ferocious intensity. The entire ring is essentially a map of that single, expanding shockwave, a brilliant circle of stellar birth tracing the path of the most violent day in the galaxy's history. The faint spokes that connect the inner core to the outer ring add another layer of evidence to this story. These are not solid structures, but complex webs of dust, gas, and some stars that were caught in the gravitational crossfire. They represent regions where the galaxy's original spiral arms were violently distorted and stretched during the collision, or perhaps where material is still slowly falling back inward from the disrupted disk, creating a fragile bridge between the galaxy's past and its dramatically reshaped present. As for the intruder galaxy itself, astronomers have identified a strong candidate. A small, irregular galaxy located just outside the main ring shows clear signs of disruption and shares a similar velocity, suggesting it is the culprit, now continuing its journey through space, bearing the scars of the encounter. The Cartwheel Galaxy is far more than just a pretty picture. It is a crucial cosmic laboratory. It provides a stunningly clear template for understanding how galactic collisions can dramatically alter a galaxy's morphology and star-forming history in one single, violent burst. Unlike the slow, grinding merger that creates an elliptical galaxy, the bullseye collision is a rapid, transformative event that preserves a clear record of the impact in its geometry. By studying the Cartwheel, we gain profound insights into the physics of density waves, shock-induced star formation, and the resilience of galactic cores. It stands as a monumental and beautiful testament to the creative power of destruction in the universe, a permanent snapshot of a moment when chaos, for a brief time, wrote its signature in perfect, brilliant circles. We have witnessed black holes launching jets and carving bubbles within their own galaxies, but these localized events are dwarfed by a cataclysm of almost unimaginable scale, an eruption that makes even the most powerful galactic geysers seem like a gentle sigh. In the distant Ophiuchus supercluster, a colossal gathering of galaxies over 390 million light-years away, astronomers have uncovered the fossil of the largest explosion ever recorded in the universe since the Big Bang itself. The discovery began not with a brilliant flash of light, but with a profound shadow. Scientists, using a combination of X-ray observatories, including NASA Chandra X-ray Observatory and the ISAXMM Newton, along with radio data from the Murchison Wide Field Array in Australia and the Giant Meterwave Radio Telescope in India, were mapping the supercluster's hot, diffuse gas. They found something bizarre: an enormous curved edge in the X-ray emission, a boundary so vast and sharp it could only be the rim of a gigantic cavity, a bubble blown into the multimillion-degree plasma that permeates the space between the cluster's galaxies. This wasn't a small void. The cavity is truly staggering, a spherical emptiness spanning nearly 1.5 million light-years. To put that incomprehensible scale into perspective, you could line up 15 Milky Way galaxies in a row, and they would just about fit across this single hole. This cosmic crater is the scar left by an eruption from a supermassive black hole at the cluster's heart, an outburst so powerful it defies easy comparison. The energy required to carve out such a titanic cavity is beyond human comprehension. Calculations based on the size and pressure of the displaced gas reveal that the blast released a staggering 5 times more energy than the previous record holder, a massive outburst in the MS-073 5.6 plus 7421 cluster, and hundreds of thousands of times more energy than a typical galaxy-scale eruption. We're talking about an equivalent of 10 billion gamma-ray bursts detonating at once, a sustained directional fury that lasted for perhaps 100 million years. The source of this almost mythical power is a supermassive black hole residing in a central galaxy within the Ophiuchus supercluster, but this event was not a typical jet like the one we see in M87. Those jets are narrow focus beams that can travel for thousands of light years. The Ophiuchus eruption was something else entirely, a failed jet, or perhaps an unfathomably powerful outburst that occurred in a denser environment. The theory is that the black hole began to launch its typical relativistic jets, but the surrounding intergalactic gas was so incredibly thick and dense that the jets could not punch through. Instead of spearing out into the void, they inflated. Like a blowtorch pressed against a block of ice, the jets transferred all their immense energy directly into the surrounding medium, heating it and pushing it outward to create a single, gigantic, and surprisingly spherical bubble. This is a crucial distinction. It shows that the influence of a black hole is not limited to the narrow cones of its jets. Under the right conditions, its power can be converted into a truly isotropic, all-encompassing explosion that reshapes the entire core of a galaxy cluster. What makes this discovery so profound and why it remained hidden for so long is its ghostly nature. This was not an explosion seen in visible light. There is no brilliant flash traveling across the universe for us to witness. The event itself is long over, having occurred hundreds of millions of years ago. We are seeing only its permanent imprint, its fossilized signature, left behind in the searing hot X-ray glow of the cluster gas. The cavity itself is dark and empty, a region of much lower density and pressure than its surroundings. It was detected because the hot, dense gas around it forms a bright, sharp rim, outlining the void in spectacular detail. The radio data provided the final, confirming piece of the puzzle. While the cavity is largely empty, its edges are lined with a faint, diffuse radio glow. This emission is a telltale sign. It comes from ultra-high-energy electrons that were accelerated during the original eruption, either by the shock waves it generated or directly by the black hole. These electrons, spiraling in magnetic fields, continue to emit radio waves eons after the explosion subsided, acting as a lingering echo of the violence that once was. This multi-wavelength detective work transformed a strange curve feature in an X-ray map into the undeniable evidence of the most powerful explosion in the modern universe. The Hoag supercluster eruption forces us to completely recalibrate our understanding of black hole feedback. We already knew that black holes could regulate their host galaxies, but this event demonstrates their power to dictate terms to an entire cluster of thousands of galaxies. By pumping an ocean of energy into the intergalactic medium, this single black hole heated the core gas so dramatically that it permanently altered the cluster's evolution, likely shutting down star formation across all the galaxies in its vicinity for eons. It is the ultimate example of a cosmic thermostat, a display of raw power on a scale that humbles every other known phenomenon and reveals that the true masters of the cosmic web may be the dark, silent giants residing at its very heart. From the explosive fury of the Hoag supercluster, we now turn to a galaxy of serene and iconic beauty, one that holds a deep and turbulent secret within its elegant silhouette. Gracing the skies of the constellation Virgo, 28 million light-years away, is the magnificent Sombrero Galaxy. Through a telescope, it is an unforgettable sight, a brilliant, bulbous core of ancient stars encircled by a perfectly symmetrical, dark and razor-thin lane of cosmic dust. This thick dust band gives the galaxy its unmistakable appearance, like a wide-brimmed Mexican hat floating in the void. For a long time, our gaze was drawn to this stunning disk, but recent observations have pierced the darkness beyond, revealing that the galaxy's true story is written not in its bright center, but in the vast, faint sphere of stars that envelops it, an immense and deeply puzzling stellar halo. Every large galaxy is thought to be embedded within a halo, a spherical cloud of stars, globular clusters, and dark matter that extends far beyond its luminous disk. Our own Milky Way has one, a relic of its ancient formation, but the Sombrero Galaxy's halo is different. It is a behemoth. It is extraordinarily massive, containing a significant fraction of the galaxy's total stellar mass, and its stars are not just old, pristine fossils from the early universe. Instead, they present a complex and bewildering tapestry. Detailed studies have revealed a stellar population with a wide, unexpected range of ages and, most importantly, metallicities. In astronomy, metals refer to any element heavier than hydrogen or helium. These elements are forged only in the nuclear furnaces of stars and are scattered into space when those stars die in supernova explosions. A star's metal content is therefore a powerful chemical fingerprint of the environment in which it was born. The presence of both very old, metal-poor stars and much younger, metal-rich stars all mixed together in the Sombrero's halo is the central clue to its dramatic past. This chemical diversity points unequivocally to a history of galactic cannibalism, a halo that forms in isolation from the primordial gas that collapsed to create the galaxy should be uniformly old and metal-poor. The jumbled assortment of stars we see in the Sombrero's halo could only have been assembled from the outside. The prevailing theory is that over billions of years, the Sombrero Galaxy has acted as a dominant gravitational predator in its region of space. Its immense gravity has relentlessly pulled in dozens of smaller dwarf satellite galaxies, stretching and tearing them apart in a process known as tidal disruption. As each victim galaxy was shredded, its stars were not absorbed into the main disk but were instead flung onto random, looping orbits, becoming a permanent part of the growing halo. Each captured galaxy contributed its own unique stellar population to the mix. Some were ancient, low-mass dwarfs that had formed few heavy elements, contributing the metal-poor stars. Others were more massive, having undergone several generations of star formation, and they donated younger, metal-rich stars to the halo. The sombrero's halo is thus a galactic graveyard, a cosmic archive built from the remnants of its many consumed companions. This violent assembly history is further corroborated by the galaxy's incredible system of globular clusters. Globular clusters are dense spherical swarms of up to 1 million stars each, and they typically orbit in a galaxy's halo. The Milky Way has a respectable population of about 150 of these ancient clusters. The Sombrero Galaxy, by contrast, boasts an estimated 2,000. This staggering number is far more than we would expect for a galaxy of its size and type, and it fits perfectly with the accretion model. Many of these excess clusters were likely the native globular clusters of the devoured dwarf galaxies, stripped away along with their stars and assimilated into the Sombrero's vast collection. The sheer quantity of these clusters serves as a direct tally of the Sombrero's past mergers, a visible record of its relentless growth through conquest. The story of the Sombrero Galaxy fundamentally changes how we view this celestial icon. It is not a serene, isolated island universe that has spun in peaceful solitude since its formation. Instead, it is the product of a long and violent campaign of galactic consolidation. Its beautiful, orderly disk represents a stable core that has managed to withstand the chaos of its growth, while its immense and complex halo is the living evidence of the turbulent processes that built it. The sombrero stands as a majestic reminder that a galaxy's present-day beauty often masks a dramatic and violent history, and that to truly understand any galaxy, we must learn to look beyond its bright center and into the faint, fossil-rich depths of its halo. Moving from the ghostly halo of the Sombrero Galaxy, we find another cosmic community that presents a different kind of gravitational puzzle, one that pits the expected against the observed in a fundamental tug of war. Just 65 million light-years away, a relatively short hop on the intergalactic scale, lies the Fornax cluster, a dense gathering of several hundred galaxies. For astronomers, its proximity makes it an ideal natural laboratory, a place where we can study the intricate dynamics of a galaxy cluster in exceptional detail. Yet the closer we look, the more a peculiar and persistent discrepancy emerges, centered on the cluster's most diminutive members and the invisible dark matter that should be holding them together. The puzzle revolves around the dwarf galaxies, the small, faint satellites that orbit the cluster's massive central galaxies like moths around a street lamp. According to our standard models of cosmology and dark matter, these dwarfs should be embedded within their own robust halos of dark matter, which would act as protective shields, allowing them to safely orbit through the cluster's harsh environment for billions of years. However, the dwarfs in Fornax are telling a very different, more distressed story. Observations reveal that many of these dwarf galaxies appear to be suffering from extreme tidal stripping. They are being stretched and torn apart by the immense gravitational forces of the cluster as a whole. Their stars are not neatly contained. Instead, they are being pulled into long, faint streams, a clear sign of violent gravitational disruption. This in itself is not entirely unexpected. Clusters are violent places. The real mystery lies in the intensity of the stripping and its specific distribution. The affected dwarfs are found even at relatively large distances from the cluster's crowded core, in regions where the cluster's gravitational grip should be much weaker. For the dwarfs to be so severely disrupted out there, the overall gravitational potential of the Fornax cluster, the depth of its gravitational well, must be far stronger and more concentrated than our other measurements suggest. Essentially, the dwarfs are behaving as if they are orbiting within a dark matter halo that is much more massive and densely packed than the one we infer by studying the motions of the cluster's brighter central galaxies or the temperature of its hot X-ray emitting gas. This creates a serious tension between two different methods of weighing a galaxy cluster. The first method relies on the concept of dynamical equilibrium. By carefully measuring the velocities of hundreds of individual galaxies within the cluster, astronomers can calculate the total mass required to keep the cluster gravitationally bound. It's similar to determining the mass of the Sun by measuring the orbital speeds of the planets. A second, independent method uses the hot gas that fills the space between the galaxies. This gas is so hot it glows in X-rays, and by mapping its temperature and density, we can determine how much mass, primarily in the form of dark matter, is needed to gravitationally confine this vast, multi-million-degree atmosphere. Both of these techniques, when applied to the Fornax cluster, give us a consistent and reasonably modest estimate for its total mass and its distribution. But the distressed state of the dwarf galaxies points to a third, much higher estimate. They are like canaries in a coal mine, sensitive indicators that the gravitational forces at play are far more intense than our primary scales are reading. This forces us to confront a critical question. Are our standard methods for weighing clusters systematically underestimating the mass in certain environments, or is there something fundamentally different about how dark matter behaves within clusters like Fornax? One compelling line of inquiry suggests that the properties of dark matter itself might be the key. The most popular model for dark matter is known as cold dark matter, where the particles are slow-moving and interact with each other, and normal matter only through gravity. This model has been spectacularly successful at explaining the large-scale structure of the universe. However, the situation in Fornax could be a hint that dark matter has properties beyond this simple picture. For instance, if dark matter particles were able to interact with each other through some unknown force, a scenario known as self-interacting dark matter, it could dramatically alter the structure of a cluster's halo. In this model, frequent collisions between dark matter particles in the dense cluster center would cause the halo to become more spherical and concentrated, creating a steeper gravitational potential that could indeed rip apart dwarf galaxies even at larger radii. The distressed dwarfs of Fornax could be the first direct evidence of this kind of dark matter physics at work, a signal that our invisible cosmic scaffolding is more complex than we imagined. Alternatively, the explanation might lie not in the nature of dark matter, but in the complex history of the cluster itself. The Fornax cluster is not a perfectly relaxed, static system. It is likely still in the process of forming, possibly through the recent infall of a smaller group of galaxies. Such a merger event would send powerful gravitational shockwaves through the cluster, stirring up the dark matter and temporarily creating conditions of extreme tidal stress that our equilibrium-based mass measurements would not fully capture. The dwarf galaxies, being the most fragile structures, would feel this violence first and most severely, acting as a sensitive record of the cluster's recent dynamical trauma. In this view, the discrepancy is not a failure of our models, but a snapshot of a specific, turbulent moment in the cluster's long life. The ongoing investigation into the Fornax cluster involves ever more precise mapping of its dark matter distribution through the subtle warping of background galaxies, a technique called weak gravitational lensing, which provides a third direct way to measure its mass. As these different observational techniques converge, the fate of its smallest galaxies will continue to serve as a crucial test, challenging our assumptions and pushing us toward a deeper understanding of the invisible forces that sculpt not just galaxies, but the vast communities they call home. Now let us turn our gaze to a cosmic creature frozen in mid-metamorphosis, a galaxy that looks less like an island and more like a life form swimming through the void. Drifting through the northern constellation of Draco, 100 million light-years from Earth, is UGC 10214, better known as the Tadpole Galaxy. Its name is a perfect description. You see a brilliant, knotted head, blazing with the blue-white light of furious star formation, and trailing behind it, an impossibly long, delicate tail of stars that stretches for a staggering 280,000 light-years. To put that tail in perspective, it is nearly 3 times the diameter of our entire Milky Way galaxy. This is not a permanent feature, it is a fleeting, dynamic sculpture, a masterpiece of gravitational artistry that tells the story of a recent, violent encounter. The dramatic shape of the Tadpole Galaxy is the direct result of a galactic sideswipe, a gravitational dance that was too close for comfort. Astronomers have identified the likely culprit, a compact intruder galaxy that swept past the tadpole in what is known as a grazing collision. Unlike the head-on impact that created the cartwheel galaxy perfect ring, this was a more oblique encounter. The intruder did not punch to the center. Instead, it swung close by, its immense gravity reaching out like an invisible hand and violently tugging on the larger galaxy structure. This process is driven by tidal forces, the same kind of gravitational differential that the moon uses to raise tides on Earth, but operating on a scale of thousands of light years and with unimaginable power. As the intruder galaxy passed, it pulled more strongly on the near side of the tadpole than on the far side. This difference in force stretched the victim galaxy, plucking billions of stars and enormous streams of gas out of its disk and flinging them into intergalactic space. The resulting tail is not a random spray of debris. It is a coherent stream, a trail of cosmic breadcrumbs that maps out the precise trajectory of the intruder's flyby. The intruder itself is now visible as a small, distorted galaxy located just in front of the tadpole's head, continuing on its journey and bearing the scars of the encounter. The collision did more than just create a beautiful tail. It triggered a profound starburst within the tadpole's head. Before the encounter, the galaxy was likely a normal, gas-rich spiral. The violent gravitational shock of the close pass sent powerful waves of compression racing through its vast clouds of interstellar hydrogen. Just as squeezing a gas-filled sponge causes liquid to pour out, compressing these gas clouds caused them to collapse under their own gravity. This ignited a firestorm of new star formation, concentrating it in the galaxy's central region, which now glows as the brilliant blue head of the tadpole. This makes the galaxy a living laboratory for studying triggered star formation on a galactic scale. The tail itself tells a different story. While it contains many older stars that were simply ripped from the outer disk, it is also rich with hydrogen gas that was pulled along with them. In isolated pockets along the tail, this gas has also collapsed to form new star clusters, creating a string of stellar pearls along the vast cosmic filament. These clusters are incredibly valuable to astronomers because they represent star formation in an unusually pristine and simple environment, far from the turbulent core of a galaxy. The existence of the tadpole galaxy offers a profound glimpse into the transient nature of cosmic structures. This magnificent tail is not permanent. The stars within it are on trajectories that will eventually cause the tail to dissipate and fade over the next few 100 million to 1 billion years. Some of the stars may fall back toward the main galaxy, while others will be lost to intergalactic space forever, becoming part of the diffuse halo of stars that surrounds galaxy groups. The tadpole will likely never regain its spiral symmetry. The encounter has permanently disrupted its structure, and it may eventually evolve into an irregular or even an elliptical galaxy. This makes it a crucial snapshot in time, a rare opportunity to study the immediate aftermath of a specific type of galactic interaction. It demonstrates with stunning clarity that galaxies are not static, immutable islands, but dynamic and evolving entities, constantly being reshaped by their interactions. The tadpole's graceful, sorrowful tail is a monument to this constant change, a beautiful and temporary signature of the relentless gravitational forces that continually sculpt the universe. Just when we think we have a handle on the grand gravitational currents of the cosmos, the universe reveals a motion so strange it seems to defy the very flow of space itself. We've seen galaxies pulled by the Great Attractor and entire superclusters flowing toward immense concentrations of mass, but these motions fit within our understanding of gravity's reach. However, at the very limits of our observational power, a more profound and deeply controversial mystery has emerged, a mysterious, coherent drift on a scale so vast it threatens to redraw the borders of the known universe. This phenomenon is known as the dark flow. Imagine the entire observable universe, a sphere of space nearly 94 billion light years across, containing hundreds of billions of galaxies. According to our foundational cosmological principle, this vast volume should on average be homogeneous and isotropic. This means that there should be no preferred direction on such immense scales. The universe's expansion should be carrying galaxy clusters apart in a statistically uniform way, with any smaller, peculiar velocities canceling each other out. The dark flow shatters this expectation. Starting in the late 2000s, astronomers studying the cosmic microwave background, the remnant heat from the Big Bang, began to notice something unsettling. They were using the Wilkinson microwave anisotropy probe, and later the Planck satellite, to map the subtle temperature variations in this ancient light. As this light travels for billions of years across the universe to reach us, it passes through massive galaxy clusters. Hot ionized gas within these clusters interacts with the cosmic microwave background photons through a process called the kinematic Sunyaev-Zeldovich effect. By carefully analyzing this interaction, scientists can measure the peculiar velocity of these clusters, that is, their motion over and above the general expansion of the universe. When a team led by astronomer Alexander Kashlinsky compiled the data for over 700 galaxy clusters, they found a staggering and inexplicable pattern. These clusters, stretching out to billions of light years away, were not moving randomly. Instead, they showed a statistically significant, coherent stream, all flowing in the same direction at velocities of up to 600 miles per second. It was as if a silent, cosmic wind was blowing these immense structures on a course that could not be traced to any known gravitational source within our observable horizon. The immediate and obvious question is, what could possibly be pulling them? The combined gravitational pull of every galaxy, cluster, and filament of dark matter that we can map falls catastrophically short of explaining this motion. The Great Attractor and the Shapley supercluster are powerful local influences, but their tug is negligible over such immense distances. The sheer scale of the dark flow is what makes it so revolutionary and so contentious. The clusters exhibiting this motion are so far away that, according to standard cosmology, they should be completely beyond the reach of any gravitational influence from within our observable universe. The gravitational force from any structure diminishes with distance, and there is a fundamental limit, a cosmological horizon, beyond which no information, not even gravity, can have reached us since the beginning of time. The existence of the dark flow therefore implies a staggering possibility that the source of this immense pull lies beyond our cosmological horizon. It suggests that our entire observable universe, everything we can possibly see, is merely a small part of a much larger structure, and that we are feeling the gravitational tide from something unimaginably massive on the outside. This something could be a colossal concentration of mass, a supercluster, or a vast exotic structure of matter and energy that formed in the wider cosmos during the initial moments of inflation. Our pocket of the universe is simply drifting in its wake. Naturally, a claim this extraordinary has been met with intense skepticism and rigorous scrutiny. The primary challenge lies in the incredibly subtle nature of the measurement. Detecting the kinematic Sunyaev-Zeldovich effect against the backdrop of the cosmic microwave background is like trying to listen for a single, specific whisper in a roaring stadium. Critics have argued that the signal could be an artifact of incomplete data or systematic errors in how the cosmic microwave background map is cleaned and processed. Perhaps unknown foreground emissions from our own Milky Way are contaminating the results, creating a false pattern that mimics a coherent flow. Other teams analyzing data from the Planck satellite have reported null results, failing to confirm the existence of the dark flow at a significant level. This has led to a heated scientific debate, with the very existence of the flow hanging in the balance. The central issue is one of statistics and methodology. Proponents of the dark flow have refined their analyses, using different catalogs of galaxy clusters and applying various statistical tests, and they maintain that the signal persists. They argue that the null results from other teams are a consequence of using different techniques that may inadvertently smooth out or subtract the very signal they are trying to detect. If the dark flow is real, its implications are nothing short of revolutionary. It will be the first observational evidence that the universe extends far beyond what we can observe, and that the initial conditions of the Big Bang were not perfectly uniform on the largest scales. Inflation, the period of hyper-expansion in the universe's first fraction of a second, is thought to have stretched a tiny, primordial patch into our entire cosmos. The dark flow suggests that the pre-inflationary universe may have been textured, with some regions possessing more energy density than others. When inflation ended, our observable universe emerged from one of these patches, but other, vastly different patches were inflated into regions now beyond our horizon. The gravitational pull from one of these other patches could be the engine of the dark flow. This concept fundamentally challenges the cosmological principle, suggesting that on the very largest scales, the universe is not isotropic and homogeneous, but is instead a chaotic and varied multiverse, with our cosmic home merely one island in an infinite archipelago. The debate over the dark flow is far from settled, but its mere possibility forces us to confront the ultimate limits of our knowledge. It stands as a tantalizing, ghostly signal at the edge of perception, a hint that the greatest structures in the cosmos may forever lie just beyond our sight, their presence known only by the mysterious currents they stir in the fabric of our own celestial sphere. While the Fermi Bubbles revealed a cataclysm on a truly galactic scale, a more recent discovery has brought our focus sharply back to the immediate neighborhood of the monster at the Milky Way's core. In 2019, astronomers using the groundbreaking Mercator radio telescope array in South Africa peeled back another layer of the mystery, revealing a pair of colossal, hourglass-shaped structures nestled snugly within the much larger Fermi Bubbles. These are the galactic center lobes, and they paint a more intimate, though no less violent, portrait of the chaos at our galaxy's heart. Think of the Fermi Bubbles as the outer cathedral, and these newly found lobes as the inner sanctum, a distinct and vibrant chamber of energetic activity located directly above and below the supermassive black hole, Sagittarius, a star. Their scale, while smaller than the Fermi Bubbles, is still mind-boggling. Each lobe stretches for about 1,400 light-years, towering over the central black hole they emanate from. What makes them so immediately fascinating is their stark, defined shape and their brilliant radio glow, which outlines a structure that looks less like a bubble and more like an exhausted pair of lungs or a cosmic hourglass, with its narrow waist pinched tightly at the galactic center. The origin of these lobes is deeply tied to the same central engine, but their distinct characteristics tell a very different story from the one whispered by the Fermi Bubbles. The prevailing theory is that these lobes are the direct result of a relatively recent, powerful outburst from Sagittarius, a star. Unlike the single cataclysmic event that may have created the Fermi Bubbles millions of years ago, the galactic center lobes point to an eruption that was both more recent and perhaps less energetic, but incredibly focused. The leading idea is a variant of the black hole accretion story. Imagine a large cloud of gas and dust, perhaps a rogue molecular cloud, drifting too close to the black hole's event horizon. As this material is torn apart and spirals inward in a frenzied accretion disk, it is heated to millions of degrees, but not all of this superheated material falls in. Some of it, channeled and accelerated by the black hole's powerful magnetic fields, is shot back out into space in two powerful jets, erupting perpendicularly from the black hole's poles. These jets, traveling at a significant fraction of the speed of light, would have plowed into the denser material of the galactic center region, inflating these giant, radio-emitting bubbles on their way out. The sharp, defined edges of the lobes suggest this was a sudden, short-lived event, a powerful burp from the black hole that lasted perhaps for a few tens of thousands of years, a mere blink in cosmic time. This discovery provides a crucial new piece to the puzzle, allowing us to see the dynamic activity of our galactic core in multiple dimensions and across different time scales. The existence of both the vast Fermi Bubbles and the more compact galactic center lobes suggests that Sagittarius, a star, is not a perpetually slumbering giant, but rather a fitful sleeper, prone to periodic outbursts of varying intensity. It operates in cycles. The Fermi Bubbles could represent a rare, epic eruption, a feast of cosmic proportions that shaped the galaxy's halo on the largest scale. In contrast, the galactic center lobes likely represent a more common, smaller-scale snack, a more frequent flaring of activity that shapes the immediate environment around the black hole itself. This layered history is like finding multiple rings in a tree trunk. Each structure records a different outburst, a different chapter in the life of our central black hole. The lobes, being smaller and more centrally located, are also subject to different environmental pressures. Their shape is likely molded not just by the initial jet, but by the intense pressure and density of the gas and magnetic fields in the crowded galactic center, which confines the outflow into its distinctive hourglass form, unlike the more freely expanding Fermi Bubbles higher up in the galactic halo. Studying these lobes offers a front-row seat to understanding how black hole feedback operates on a local scale. The energy deposited by such an outburst heats the surrounding gas, preventing it from cooling and collapsing to form new stars. This means that even these smaller scale events from Sagittarius, a star, play a critical role in regulating star formation in the very center of our galaxy, effectively putting a ceiling on how many new stars can be born in its immediate vicinity. The ongoing analysis of the galactic center lobes is a vibrant area of research. By measuring their exact size, energy content, and expansion rate, astronomers can work backward to calculate the power and duration of the black hole outbursts that created them. This, in turn, helps us understand the diet and behavior of Sagittarius, a star over recent millennia. The lobes stand as a brilliant, radio-lit testament to the fact that our galactic center is a dynamic and ever-changing environment, where even the quietest of black holes has a dramatic and impactful voice, periodically reminding us of the immense forces slumbering at the heart of our celestial home. And so our journey across the cosmos concludes, having taken us from the silent, invisible halos that cradled galaxies to the violent, echoing aftermath of the largest explosion since the Big Bang. We have stood in awe of perfect rings born from chaos, witnessed galaxies stretched into cosmic tadpoles, and felt the unsettling pull of a dark flow from beyond the known universe. Each of these 25 structures, from the serene geometry of Hoag's object to the terrifying power of the Ophiuchus eruption, represents a fundamental question mark etched into the fabric of reality. They are not mere anomalies, they are the frontiers of our understanding, the places where our most cherished models of physics and cosmology are stress-tested to their absolute limits. The sheer diversity and profound weirdness we've encountered prove one thing beyond any doubt: the universe is a far more inventive, chaotic, and wondrous artist than we ever dared to imagine. It is a realm where nothingness itself, in the form of the Boötes void, becomes a dominant feature, and where a galaxy can possess the mass of a titan, yet where the faint glow of a ghost, as with Dragonfly 44. These are not problems to be solved and filed away, they are catalysts, each one, from the faint whisper of the Wow signal to the monumental challenge of the Hercules Corona Borealis Great Wall, is a beacon guiding the next generation of telescopes, the next revolutionary theory, the next leap of human curiosity. They remind us that science does not advance by confirming what we already know, but by relentlessly pursuing everything we do not. Now, we turn this final reflection over to you. After traveling across billions of light years and witnessing these 25 cosmic puzzles, which one left you the most utterly baffled? Was it the haunting perfection of the Red Rectangle Nebula, a dying star's final, geometric masterpiece? Or the relentless, mysterious current of the dark flow, hinting at realities beyond our horizon? Perhaps it was the raw, creative destruction of the Cartwheel Galaxy, or the silent, overwhelming dominance of dark matter in the sombrero's halo. Share your thoughts and your favorite cosmic mystery in the comments below. We are all explorers here, and the conversation is just beginning. If this journey through the universe's greatest enigmas has left you hungry for more, be sure to subscribe so you don't miss our next voyage into the secrets of the cosmos. The universe is vast, its mysteries are endless, and the next great discovery is always just over